Hey everyone. So let's talk about Chapter 10. This is the t-test for 2 independent samples. So this builds on Chapter 9 when you learned the t-test for an independent sample. So that was just the one sample that you were comparing to the population. So I just want to review what you learned in Chapter 9 real quick before we get into Chapter 10. So in Chapter 9, you learned the t-test. And in that test, you took the sample mean and you compared it to the population mean. And then you divided by standard error. And if you remember, standard error was calculated by taking the standard deviation of the sample and dividing it by the square root of the sample size. So we're going to build on that in Chapter 10 because this is what you do when you compare 2 independent samples. So this would be like if you have 2 groups or if you have 2 levels of the independent variable or something like that. So everything that we've covered so far dealt with only one sample, like I mentioned. When we talked about the z-scores and the t-test in Chapter 9, all of that was one sample. And moving forward, we're going to compare 2 or more sets of data, which is what we usually do with some kind of hypothesis test. In research methods, when you learn about different research designs, one of the designs that you cover a lot are factorial designs, where you have an independent variable and a dependent variable. So this is the type of test that could compare 2 levels of an independent variable. You probably remember this from research methods as being called a between subjects design, where I have 2 different groups, they get 2 levels of the IV, and then I'm comparing some sort of dependent variable between them. So an example would be where you have 2 sets of people. I give one group the first level of my independent variable. In this case, I'm giving them some kind of passage to read from a tablet. And my second level of the independent variable is reading from a book. And then my DV would be something like reading comprehension. And I want to see if reading comprehension differs between the 2 types of reading material. On the one that I just showed you, we do the variance divided by n. So I do the division, and then I do the same thing for group 2. So I do the variance divided by n for group 2. Then I add those 2 together. So I do division, division, then addition. Different with pooled variance, because in pooled variance I'm doing addition, addition, and then division. So just make sure you are copying down the formulas exactly and making sure that you are putting the numbers in the right place. Okay, and notice that the symbol for pooled variance is the same as the symbol for variance. Remember, variance is little s squared. So pooled variance is little s squared, but we have a subscript p. And so that subscript p is telling me that this is pooled. So it's the label, right? The p is the label. So once I get my pooled variance, I'm actually going to use that to calculate the estimated standard error. So you'll notice that instead of the variance for group 1 and the variance for group 2 in the formula, I'm actually using the pooled variance for both of them. So this is the same formula that you saw 2 slides ago. The only difference is that pooled variance has replaced individual variances. So when I have 2 samples of different sizes, I pool the variance together to give more weight to a larger sample size. And then once I get my pooled variance, I plug it into the formula for standard error. And so the formula is the pooled variance divided by the sample size of the first group plus the pooled variance divided by the sample size of the second group. And then I get the square root of the whole thing. Now, I mentioned degrees of freedom a minute ago, but in this case, degrees of freedom with two separate samples is the total n minus 2, because for each separate group, I'm taking n minus 1. The basic elements of the t-test that you learned in Chapter 9 are just the same here. The only difference is that things are doubled. So this chart is comparing the single sample t-test to the independent measures t-test. So in a sample that I'm comparing to the population, I simply have one sample mean. But in independent samples t-test, I have two sample means. And I'm comparing them to a hypothesized population parameter, which, remember, the null hypothesis is that this equals 0. And so I actually don't have to plug that into my formula. The standard error is expanded. It's just the same but doubled, and I use pooled variance when I have different sample sizes. And then finding the variance is the same, it's just doubled, and I have a new symbol because I have a symbol for the pooled variance. So I know that this is a lot of formulas. Make sure when you're doing the mind tap that you have all of these formulas written down so that you can refer back to them, because there's a lot of formulas. So you should write it down with the labels so that if you forget what that little p means, you'll have the label right there to remind you that, oh yeah, that's the pooled variance. Each of my groups is a degrees of freedom of 7, right? Because it's n minus 1 for each group. So I have my critical region was 2.145. And hopefully, okay, so the mean was 8 minus 12. And so our mean difference was, the mean difference was -4. And I don't remember the pooled variance. Was it? I don't know. I erased it. Or not the pooled variance. Oh. It was 1.5, right? Because it was the square root of 2.25. So the standard error, I think, was 1.5. Okay, so let's see if we can get it right. So we have -4 for the mean difference and 1.5 for the standard error. So let's see. To the slide. Okay. So the mean difference was -4. And we're going to add and subtract our standard error of 1.5 times the t value for how confident we want to be. Oh, I don't have that either. Well, let's see. Anyway, I don't actually know. But here's 4, so that's our mean difference. And so whatever the number is, 1.5 times whatever the t is, if we take that number and we add and subtract to 4, well, because we can add and subtract it to 4 or -4, it doesn't matter. That's the number that goes here, right? We subtract it and we get 0.782, or we can add it and we get 7.218. Now, what we're hoping to find is that this confidence range does not include 0, because 0 is the null hypothesis. So if my confidence interval included 0, then that means that I'm 95% sure that it could also be no difference, right? And so if that was the case, I would not be able to reject the null because that's in my range of confidence. But in this case, my confidence range does not include 0, so I can reject the null hypothesis, and I can conclude that people do report different amounts of puzzles if they are in a well-lit room versus a dimly lit room. Now, sample variance and sample size are really important for the independent measures t-test. They both directly affect the t-statistic. Because if I have more variance, then I get a larger standard error. So that means that I get a smaller t-result. And so it's less likely to be significant. A larger sample size, on the other hand, gives me a smaller standard error, and I would get a larger t-result. So I have more of a chance of rejecting the null hypothesis. So less variance and a larger sample size are better for getting a bigger t-result. Here's 2 examples. So in this first example, I have the same sample size, 9 and 9, and I have a mean of 8, and then in treatment 2, I have a mean of 13. And I have the same variance in each case. So I can clearly see a difference from treatment 1 to treatment 2. Treatment 2 is definitely higher than treatment 1. There's no overlap. There's clearly a difference. And so if I were to calculate the t-value, I would probably have a significant difference between treatment 1 and treatment 2. So remember that the means are 8 and 13. Now let me erase the ink. In the next example, the means are the same. I have a mean of 8 and a mean of 13. And my sample sizes are the same. And my standard deviations are the same for each group, just like they were before. But my standard deviations are really large. And as you can see from the data, there's no clear pattern. Treatment 1 and treatment 2 overlap. So my 2 independent groups overlap. I cannot clearly see that one of my groups is better or higher than the other group because they're all over the place. So in this case, there's a lot of variance, and so my t-value would be pretty small. I would probably not be able to see a clear difference, and I would not be able to reject the null and conclude that I have a difference between my 2 treatment groups. So that is chapter 10.